तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
We have seen some duality in the relations between the Laplace transforms and time functions. For example, differentiation in time domain corresponds to multiplication by s in the frequency domain. Similarly, differentiation in the frequency domain corresponds to multiplication by t in the time domain. You recall t f of t as Laplace transform minus d by ds of f of s. We have also seen that integration in time domain corresponds to division by s in the frequency domain essentially, that is integral f of t dt corresponds to f of s over s. In a dual way, if we have f of t upon t, it must correspond to integration in the frequency domain. This is a property which is not particularly useful, but it may be useful in some special situations. Just let us look at this rule. We have let f of t and f of t upon t be Laplace transformable. And let the integral s to infinity of f of s ds exist. So, this integral exists. What we mean by s to infinity is, suppose this is the region of convergence of the Laplace transform of both f of t and f of t by t collectively. Then we take any point s here and then integrate this f of s over some contour starting from point s in the region of convergence up to infinity, so that the real part of s goes to infinity. That means when you take s is equal to infinity, that means at least the real part of s is going to infinity. So, one can possibly say that the point on the x axis out at infinity is the ending point at this. So, if you do that, then the theorem states that f of t upon t has the Laplace transform s to infinity of f of s ds. This is the rule, and since we are talking about s, so we may as well, to make it clear, it can be a dummy variable z, f of z dz, where z is a complex variable, and once you make the integration, it is a function of s, because s is a limit here. So, this will be a function of s. Proof of this is again is straightforward. S to infinity of f of z dz can be written as s to infinity f of z dz. I can write this as, this is the Laplace transform of f of t, therefore 0 to infinity f of t. Instead of f of s, I am writing f of z, therefore I must write e to the power of minus zt dt. This will be f of z. The integration is with reference to t, of course. This is t equals 0 to infinity, and dz. And this first integration is with reference to t, second integration is with reference to z. Now, if I reverse the order of integration, I will say t equals 0 to infinity f of t. So, whatever functions are there which are independent of z, I will pull them outside. So, f of t dt, then s to infinity of, you have got e to the power of minus zt dz, and this will be t equals 0 to infinity f of t dt. This integral will be e to the power of minus zt. You recall that you are integrating with reference to z, therefore t is a constant, therefore minus t, and you with the limits to infinity. That is what you are having. And in the upper limit, e to the power of minus zt goes to 0 because you are taking this integration from s equals 0 to point at infinity along the x axis, let us say. Therefore, for positive values of time, because this integration involves only positive values of time, therefore, when positive t is there and the real part of z goes to infinity, then this becomes 0 at the upper limit. At the lower limit, it will be e to the power of minus st by minus t. Therefore, this will be t equals 0 to infinity f of t dt, and this will be e to the power of minus st by t, because we are taking the lower limit, therefore this minus sign is absorbed by another minus sign coming out in front. Therefore, this is what we are having. This will be 0 to infinity of f of t upon t e to the power of minus st dt, and this is indeed the Laplace transform of f of t over t. This is the Laplace transform of f of t over t. So, Laplace transform of f of t over t is this integral. So, division by t in the time domain corresponds to integration in the frequency domain, just like integration in the time domain corresponds to division by s in the frequency domain. As I mentioned, this rule is not particularly useful to us in our context, in our applications to networks. So, we will just record this as a dual rule to the rule for integration in time domain and leave it at that. In solution of networks, transients and systems, sometimes we may not be interested in finding out the entire function of time from its Laplace transformed variable, which is Laplace transform which is available from the solution of a network. We would be interested in finding out the initial value of f of t or its derivative, first derivative or second derivative, without having to find out the entire function of time f of t. Suppose f of s is given, we would like to know what is f of 0 plus, or what is the initial value of the derivative of f with reference to time at t equals 0 plus, without our having to find out the entire f of t for all time t. Now, this can be done using a property of Laplace transforms, which is known as the initial value theorem. Now, let the conditions for this f of t and the derivative f prime t are Laplace transformed. Laplace transforms exist for both these. Further, limit as t goes to 0 plus of f of t exists. Suppose these conditions are fulfilled, then limit as t goes to 0 plus of f of t, which we will write simply as f of 0 plus, is given by limit as s tends to infinity of s times f of s. This is the statement of the initial value theorem, that the initial value of a time function is given by limit as s tends to infinity of s times f of s. This limit is quite easy to evaluate, because once you have a rational function as s tends to infinity, you have to take the ratio of the two leading coefficients in the numerator and denominator. That will be limit, and that is equal to f of 0 plus. Now, what is the proof for this? Let us say we are trying to find out the Laplace transform of f prime t. So, it is f prime t e to the power of minus st dt 0 to infinity, 0 minus to infinity. That is the Laplace transform of the derivative of f of t. According to what we had already discussed, this will be s f of s minus f 0 minus. According to the rule for finding the derivative Laplace transform of the derivative of a time function, this is what we are having. The Laplace transform of the derivative of this is equal to SFS minus F0 minus. Now this integral can be split in two parts, 0 minus to 0 plus of f prime t d e to the power of minus st dt plus 0 plus to infinity of f prime t e to the power of minus st dt. That of course is equal to S f of s minus f0 minus. Now as far as this integral is concerned, this is evaluated over a very tiny interval from 0 minus to 0 plus. So the value of t in this portion is equal to 0, therefore this will be equal to 1 in this interval 0 minus to 0 plus is essentially 0 f e to the power of minus st where t equals 0 is equal to 1. Therefore you are really integrating f prime t dt from 0 minus to 0 plus. So the value of this will be f0 plus minus f0 minus. That is what you are having. In addition, you are having this additional function 0 plus to infinity f prime t e to the power of minus st dt. So when you combine these two, if f0 minus gets cancelled out, then you are having, equating these two, you get 0 minus plus to infinity of f prime t e to the power of minus st dt equals plus f0 plus equals s times f of s. This is also something which we would have straight away written, because Laplace transform of f prime t starting from 0 plus onwards, we said Laplace transform of that is S f of s minus f0 plus, something which we already observed when we are talking about the differentiation rule. So we did not have to derive this, but my purpose in doing it in this fashion is something which we will explain a little later. Now in this, let us take the limit, take limit as s goes to infinity. Now we take the limit as s goes to infinity such that the real part of s goes to infinity, positive infinity, that is along the, say along the real axis for example. Then when you take the s goes to infinity, because f prime t is Laplace transformable and you are taking s going to infinity and we are talking about positive values of time, this is an exponential order, therefore this will become 0. This becomes 0 as s goes to infinity for positive t, such that the real part of s goes to infinity, therefore this becomes 0, therefore this integrand becomes 0, so this will be 0. If you do that, this will be 0 and you have f0 plus equals limit as s goes to infinity of s times f of s. That is what we wanted to prove. Now so your s must tend to infinity such that the real part of s goes to infinity. That means if this is the region of convergence that you are having here, whatever it is, s goes to infinity either in this direction or this direction, so that the real part of s must go to infinity. That also is important. That means you must take the value of s going to infinity either in the first quadrant or the fourth quadrant. So real part of s must go to infinity. That is something which you have to keep in mind. Now for this theorem to be valid, so f t and f prime t must be Laplace transformable as already mentioned. Limit as t goes to 0 plus of f of t should exist. That means you cannot have the Laplace transforms of this. For example, if you have a constant, for example, an impulse for example at the origin, then you cannot have this Laplace transform for this. I mean the initial value theorem will not apply for that. Now the reason why I started with this integration from 0 minus is, whether you define the Laplace transform starting from 0 minus or 0 plus, the initial value theorem will always give you limit as s tends to infinity of s of f of 0 plus only. it can't give you f of 0 minus. Sometimes people may like to think that if the Laplace transform is defined as 0 plus to infinity of f of t e to the power of minus st, then if that f of s, you take s f of s, take the limit as s tends to infinity, it will give 0 plus. But if we had taken the Laplace transform f of s to be starting from 0 minus, then the limit as s tends to f of s, as s tends to infinity of s times f of s will give f of 0 minus. No, whether you define the Laplace transform as starting from 0 minus or 0 plus, the initial value theorem will give you only this condition, f of 0 plus only, it can't give you f of 0 minus. So that is why I want to make that very clear. That's why I started with the definition of the Laplace transform starting from 0 minus. So even if you start with 0 minus, the initial value theorem will give you only 0 plus. Let me give you a few examples. One, suppose I had f of s as 0.9 s plus 1, 2.1 s squared plus 5s plus 16. So this is f of s, and through various techniques which we know already or which we will discuss later, you can find f of t. But suppose we are not interested in finding f of t, we want to know what is f0 plus. The function of time as the origin is approached from the positive side, f0 plus. For this we do not have to find out the f of t. This initial value theorem tells us that limit as s tends to infinity of s times f of s, which is 0.9 s squared plus 0.9 s divided by 2.1 s squared plus 5s plus 16. And as I said, when you take limit as s tends to infinity as s f of s, we can take s to be approaching infinity along the positive x axis. So that means we can take only the ratio of the two leading coefficients, because these become insignificant compared with the first term as s becomes larger and larger, and therefore 5s plus 16 becomes insignificant compared with 2.1 s squared. Therefore, as s goes to infinity of, again here I must put limit as s goes to infinity of this will be simply 0.9 divided by 2.1. That is what it is, whatever that might be. So initial value theorem will enable us to find out the initial value at t equals 0 plus of a function of time from its Laplace transform without our having to go through the ordeal of finding out f of t from this. Let us take another example. F of s is s plus 1 over s plus 2. Now limit as s tends to infinity of s times f of s equals s squared plus s over s plus 2, and this goes to infinity, because as s goes to infinity, s squared upon s will become essentially equal to s that goes to infinity. Now that violates this condition. Limit as t 0 plus f of t exists, that condition will not be that will be violated. That means this is actually what will happen is this is an impulse 1 minus 1 over s plus 2. F of s is 1 minus 1 over s plus 2. That means f of t here is delta t minus e to the power of minus t t u t. So because of the delta function, this initial value theorem is not valid here. Initial value theorem is not valid. So we will say that whenever delta functions exist at the origin, we will not have the initial value theorem applicable in such situations, because it leads to infinity, whatever it might be. So it is not very useful unless you talk about infinity of the magnitude, because that makes it a little more complicated. So we will say whenever this limit leads to infinity, which means f of t has impulse functions here, it will not, the initial value theorem will not be valid. Okay, so let us Now consider the dual rule of this, which gives the final value of a function of time without our having to find out the inverse Laplace transformation. We have seen in the initial value theorem that the behavior of f of s at s equals infinity essentially governs the value of f of t at t equals 0. As a dual to this, the behavior of f of s at s equals 0 will essentially dictate the value of f of t when t goes to infinity, and that is given by the statement of what is called the final value theorem. It says like this: if f of t and f prime t are Laplace transformable, both are Laplace transformable, and s times f of s has no poles on j omega axis and in the right half plane, I will write this in the right half plane, then limit as s tends to 0 of s times f of s equals limit as t tends to infinity of f of t, or you can say that is the final value of the time function f of t. So, you take the limit now as s goes to 0 of s times f of s, that will give you the final value of the function of time f infinity. Now, we say s of f s has no poles in the j omega axis in the right half plane. That means, if you plot in the complex plane, this must be the region of analyticity of s times f of s. So, s times f of s has no poles in the hatched area. If you have a pole on the imaginary axis or in the right half plane, then the particular theorem is no longer valid. Proof is again straightforward. We have 0 minus to infinity of f prime t e to the power of minus s t dt. That is the Laplace transform of the derivative of f of t is s times f of s minus f 0 minus, according to our Earl rule. Now, take limit as s goes to 0. S goes to 0. This will be, then if s goes to 0, this will become 1. This will become 1. So, that means you are essentially integrating f prime t from 0 minus to infinity. So, when you are integrating f prime t, this becomes f of t, you are taking the limits between infinity and 0, that means f infinity minus f 0 minus. This is what you are getting here. And on the other hand, you are having a limit as s goes to infinity, s goes to 0 of s times f of s minus f 0 minus. So, if you take the limit as s goes to 0 on both sides, this is what results, and you cancel these two terms, and this is what you are having. F infinity as t goes to infinity, limit as t goes to infinity of f of t, which we call f infinity, is limit as s goes to 0 of s times f of s. This is again a dual rule to what we had earlier observed as the initial value theorem. Examples. A. Four upon s over s plus 1. This is f of s. Now, we would like to know whether we can find f infinity without having our finding out f of t. So, limit as t goes to infinity of f of t, which we write for convenience as f infinity simply. This will be limit as s goes to 0 of s times f of s, which means 4 upon s plus 1. So this is 4. That is all. So the final value of the time function is 4 units. We did not have to really find f of t. Let us take another example, B. This tells us that the advantage of this theorem is, without having to find out a particular analytical expression for f of t from f of s, which sometimes can be complicated, we can straight away find out the final value without having to go through this intermediate step of finding f of t. Let us take f of s as 4s plus 91 divided by 123s squared plus 63s. Once again, we wish to show that f infinity can be found out without having explicitly to find f t with these awkward numbers. So f infinity now is limit as s tends to infinity 0 of s times this, which is 4s plus 91 divided by 123s plus 3, because when you multiply this by s, this s squared will become s, and that other s gets dropped out. This becomes 63. So this is 91 by 63. Third example, f of s equals s over s square plus 1. Suppose this is of course cos t, we know that, cos t ut. The initial value the final value theorem, if you like to apply for this, you must multiply this by s and then take the limit as s goes to 0. This will tell you limit as s goes to 0 of s times f of s is of course 0. But then what is the final value of cos t? We can't say what it will be. It will, because it's going on oscillating between plus 1 and minus 1, right? So if you take the average of that, it may be 0. But then the point to observe here is, this does not satisfy the statement of the theorem. S f of s has no poles on j omega axis. So if you take s times f of s, this will be s squared over s squared plus 1. S squared plus 1, s squared over s squared plus 1 will have poles at plus or minus j1. Therefore, initially the theorem does not apply. So the final value theorem does not apply in this case, and therefore whatever limit you get may or may not be true. Therefore we cannot use this wherever s times f of s as poles either on the j omega axis or in the right half plane. So this is a situation where the theorem is not valid. Similarly, if you have 1 over s squared plus 1, then also the theorem is not valid, because for the same reason that sin t, you can't find out the final value of sin t. You can only assume it is 0 because an average, but that is not a very rigorous statement. We shall now consider another important property which is useful in system studies, particularly when you want to find out the response to an arbitrary input when you know the response to an impulse input through the medium of convolution integrals. So we would like to know how the convolution in time domain, how it transforms itself in the S domain. Convolution in time domain. This is sometimes referred to as real convolution. This is said to be real convolution in the sense that we are carrying out this convolution in time domain, which is a real variable, not in the transform domain, which is a complex variable. So this is real convolution. You recall that f t convolved with g of t is, the definition is f of tau g of t minus tau d tau. You can also write this as f t minus tau g tau d tau. these are both are equivalent, and you take the variation of tau from minus infinity to plus infinity in a general case, and for causal functions where f t and g t are causal time functions, you take the limits, because f tau has a value only from tau equals 0 onwards, possibly f of tau as a f of t has an impulse at the origin, we take 0 minus to start with, and then when tau exceeds t, this becomes negative, therefore there is no point in carrying out the integration beyond t equals tau or tau equals t, and therefore we take this as t, then f tau g t minus tau, and to take care of possibility of an impulse in g of t at the origin, we take this as t plus. So this is what we are having by means of the meaning of f of t convolved with g of t. Now let us try to find out the Laplace transform of this. So Laplace transform of f tau g t minus tau d tau 0 minus to t plus, that is what we are seeking. So this will be 0 minus to infinity of this quantity, 0 minus to infinity t plus f tau g t minus tau d tau, and this integration is carried out on tau, and the whatever results is a function of t, you multiply it by e to the power of minus st dt. This integration is with reference to t. So that is the definition of the Laplace transform of the convolution of the two time functions f t and g t, which are assumed to be causal. Now I would like to do the integration first with reference to t and then go to tau later. Therefore to do that I have also a function t plus here. So to avoid that, what I can do is I will have e to the power of minus st dt, because I would like to do the integration with reference to, I will do the integration with reference to tau itself to start with. Tau equals 0 plus to t plus. Now f of tau g t minus tau, suppose I introduce u t minus tau d tau, t equals 0 minus to infinity. Now u t minus tau is going to be 0 when tau exceeds t. When tau exceeds t, u t minus tau is 0. Therefore this integrand will become 0 when tau exceeds t. Therefore I can, instead of having t plus, I can as well have infinity. Now that I have introduced this symbol u t minus tau here, I may as well take the limit of integration of tau from 0 to infinity. This is 0 minus, 0 minus. So to ensure that the same integral is valid even here, the values of the two integrals are the same, I have introduced purposely u t minus tau and took the limit as up to infinity, because the value of u t minus tau is going to be 0 for tau greater than t. The reason why I did this, because we would like to relate them to the Laplace transform integrals. Therefore the limits must be from 0 to infinity. So in order to have that kind of property, I have to purposely introduce this. All right, f t minus tau d tau. Now this will be equal to zero minus to infinity. Now I would like to interchange the limits of integration. This is originally the first integration with reference to tau, next integration with reference to t. Now suppose I reverse the roles. So I do the integration with reference to tau later and then do the integration with reference to t first. So whatever you are having as constants whenever we are integrating with reference to t can be brought outside, which is f tau is 1 for example, d tau can be brought outside, and all functions which are involved with t are to be taken into account in the first integration. That will be gt minus tau ut minus tau e to the power of minus st dt, e to the power of minus st dt. Now this is the Laplace transform of a function, delayed function gt delayed by tau seconds. If the Laplace transform of g of t is g of s, Laplace transform of the delayed time function t minus tau is e to the power of minus s tau times g of s. If g of t has for its Laplace transform g of s, g of t ut as the Laplace transform of g of s, g of t minus tau ut minus tau as Laplace transform g of s times e to the power of minus tau s. That is something which you already know. Therefore, we can write this as tau equals 0 minus to infinity of f tau d tau g of s times e to the power of minus s tau d tau, sorry, d tau comes from here. Now in this, g of s is a constant, therefore g of s times tau equals 0 minus to infinity of f tau e to the power of minus s tau d tau. Oh, I am writing d tau twice here, it's not necessary. And this is indeed f of s. F of t e to the power of minus st dt integrated from t equals 0 minus to infinity is f of s. Instead of t we have the dummy variable tau. Therefore, this is f of s multiplied by g of s. So the neat result that we are having here is finally that f t star g t star, the convolution of two time functions f t star g t star as the Laplace transform, the product of the two corresponding Laplace transforms. So this is the important result. Convolution in the time domain corresponds to multiplication of the respective transforms in the frequency domain or the complex frequency domain, S domain. This is quite neat, and this is a rule which will be useful for our work, as I said, in system studies, where when we know the impulse response h of t, to find out the response for an arbitrary function of time, all we have to do is Laplace transform of the output will turn out to be the product of the Laplace transforms of the impulse response and the input function. Example. Let us consider an example. Suppose I have 1 over s plus 1 times s plus 2. Now we can split this up as 1 over s plus 1 multiplied by 1 over s plus 2. So this f of s is the product of two functions, and suppose I call this 1 over s plus 1, the inverse Laplace transform of that is e to the power of minus t ut. Let me call this as f1 of t, or simply f of t. The inverse Laplace transform of this 1 over s plus 2 is e to the power of minus tt ut. Let me call this g of t. So the product of these two Laplace transforms must correspond to the convolution of these two time functions f of t and g of t, because convolution product in the time domain is equivalent to multiplication in the transform domain. So the inverse Laplace transform of that is f t star g t star. F t star times gt, ft star gt. So that will be 0 to t. When there are no impulses present, we may start with 0 and t instead of 0 minus and t plus. We can simply say 0 to t of f of tau gt minus tau d tau. So 0 to t f tau e to the power of minus tau u tau and gt minus tau. G is e to the power of minus tt ut, therefore e to the power of minus 2t minus tau ut minus tau. Now in the range of integration, when tau goes from 0 to t, this is equal to 1, u tau is equal to 1, because tau takes only positive values of time, tau positive values, and ut minus tau also the argument, the t minus tau is going to be positive because tau is going to be less than t, therefore this is also equal to 1. So we need not regard them, we need not pay any attention to them. Now the integration is only with reference to tau, therefore e to the power of minus 2t is a constant as far as that integration is concerned. So you can pull this outside the integral sign. So you have 0 to t of you have u e of minus tau multiplied by e of plus 2 tau, therefore it is e tau, e of minus tau multiplied by e to the power of plus 2 tau, so e tau d tau. That means this is e to the power of minus 2t, the integral of this is e to the power of tau itself by 1 with the limits 0 and t. So that will be e to the power of minus 2t e to the power of t minus 1, and that will be e to the power of minus t minus e to the power of minus 2t, and this is valid for t greater than 0, because in all our arguments if t is greater than 0 only we have assumed to take ut minus tau and u tau to be equal to 1. Therefore for t greater than 0 it is e to the power of minus t minus e to the power of minus 2t, and therefore this particular Laplace transform has got by its inverse Laplace transform e to the power of minus t minus e to the power of minus 2t. Now we wanted to illustrate this as an application of the convolution theorem. You can get at this result even simply by considering this, by making partial fraction expansion, which we will talk about in greater detail later, but this can always be expressed as 1 over s plus 1 plus 1 over s plus 2, and you can write this as 1 minus 1. So if you consider this, you have a common denominator, it will have s plus 2 minus of s plus 1, that will be 1. So this is equal to this, and we know that the Laplace inverse Laplace transform of this is e to the power of minus t ut, and the inverse Laplace transform of 1 over s plus 2 is e to the power of minus 2t ut. So this is exactly the result that we have obtained here in a more direct fashion, in a simpler fashion. But I wanted to illustrate the application of the convolution theorem by considering this as a product of two transforms, and in the time domain it turns out to be the convolution of two time functions. This is a verification of our result. So we have seen that the convolution in time domain corresponds to multiplication of the respective Laplace transforms in the frequency domain. As a dual rule, we have convolution in complex domain, convolution in S domain. This is called complex convolution. I will just mention this rule and leave it at that. We will not pursue this because it's rather difficult to apply, and we don't have really necessary to use this a great deal. Therefore, I will simply say that if you multiply two time functions ft and gt, multiplication in time domain corresponds to convolution in the frequency domain. F of s convolved with GFS. What is meant by this convolution in the frequency domain is an integral which is like this 1 over 2 pi j c minus j infinity to c plus j infinity of f of z times g of s minus z dz. So, you do an integration of the product f z times g of s minus z, where z is a running variable, and therefore, this entire integral will be a function of s, and that would be the Laplace transform of the product of f of t g t. And we have to take c, the abscissa of convergence for this sigma c must be greater than the abscissa of convergence for the function f of t, Laplace transform of f of t, Laplace transform of g, and Laplace transform of delta f delta sigma f plus sigma g. This abscissa of convergence for the product f of t g t Laplace transform must be larger than this, all these. So, whichever is the maximum, that should be smaller than sigma c, and this contour integration c should be larger than sigma f, and then should be sigma minus sigma g. That means, actually what it turns out is you have to take this contour integration in a narrow band separated by two regions. But as I said, we will not pursue this. All we can say is that multiplication in time domain corresponds to convolution in the frequency domain. Those of you who are interested can look up the reference books on this, and you will get further details on this, but we will not pursue this. We will now take up an interesting application of the Laplace transforms, which we will also treat this as a property of the Laplace transforms of periodic functions of time. Laplace transforms are periodic functions of time. Suppose I have a periodic function of time which is given by like this 0 to t naught, 2 t naught, 3 t naught, etc. This is f of t. Now consider one period of this blank. This I will call this f t multiplied by u t multiplied by minus u of t minus t naught. That means you are multiplying this by a gate function u of t minus u of t minus t naught. That is just a pulse like this of unit amplitude. If you multiply this with this, you get this. So, this we will call that f1 of t. So, if you take a single pulse, the variation of the f of t over one particular period only, if you know the Laplace transform of this, you can find the Laplace transform of this easily. It goes like this. Suppose f1 of t has the Laplace transform f1 by of s. That is a single pulse, let it have the Laplace transform f1 of s. Then what is the Laplace transform of f of t? F of t is this pulse plus second pulse plus third pulse. Each pulse is displaced by this by an amount equal to t naught. The Laplace transform of this is f1 of s. The Laplace transform of the second pulse, the variation over the second period, is f1 of s times e to the power of minus t naught of s. The Laplace transform of the third pulse is f1 of s times e to the power of minus 2 t naught s, and so on and so forth. So, the entire periodic pulse function will have 1 plus e to the power of minus t naught s plus e to the power of minus 2 t naught s, etc., and this can be put in the form f1 of s over 1 minus e to the power of minus t naught s. So, if you have a periodic function of time, you want to find out this Laplace transform, all you need to do is consider the Laplace transform over one period, or the variation over one period. If its Laplace transform is f1 of s, the Laplace transform of the entire periodic function is f1 of s over 1 minus e to the power of minus t naught of s, where t naught is the period of the particular waveform. to sum up, we have in this lecture considered further interesting properties of the Laplace transform. In particular, we have considered the Laplace transform of f t upon t. Given the Laplace transform of f of t, how we can find the Laplace transform of f of t over t. Then we considered the initial and final value theorems, which enable us to find out the initial value and the final value of function of time without from their Laplace transforms, without having to find out f of t explicitly. Then we also talked about the convolution properties. Convolution in time domain corresponds to multiplication frequency domain are the two particular transforms, and the convolution in frequency domain corresponds to multiplication in time domain. The latter one we said is of limited interest to us, and then so we did not pursue this in some detail. We also observed that if we have a periodic function, it is enough if you find the Laplace transform over one period, then you can use that information to find out the Laplace transform of the entire periodic function by multiplying that, the Laplace transform of one period, by 1 over 1 minus e to the power of minus t naught of s, where t naught is the period of the periodic function of time. In the next lecture, we will work out several examples illustrating the application of the various properties that we have discussed so far.